Hello, good morning, good evening, good afternoon, everybody, wherever you might be. And most importantly, from Gia, Brazil. We are very happy to have a speaker from Floripa, ALCIDES. He will tell us everything and more about amenability of Non-Hausdorff, but Étale Groupoids, and the nuclearity of various sister algebras. So it's all yours. Take it away.
Thank you, Piotr. Thank you very much for the invitation, all the organizers. Very happy to give this talk. So, yeah, let's start. So, already mentioned, so be talking about amenability and nuclearity of Groupoids sister algebras, especially the non-Hausdorff ones. So this is, I should say, it's already there. So it's joint work with Diego Martinez. We are actually still, it's sort of a still progress work, still improving, but essentially finished already in the archive available. So yeah, this is about this paper. So in this talk, we are going to give some short introduction, motivation, and then shortly also introduce these groupoids, Étale groupoids, and their sister algebras. We're going to talk especially about non-Hausdorffness and the so-called dangerous points, which are the points that you like witness the non-Hausdorffness of the groupoid. And we are going to look at certain algebras of Borel functions, not just continuous. And this is necessary in the non-Hausdorff world. And so we are going to have some examples and some applications. Okay, so in the classical context, so many years ago, I'll mention in the next slide. So for groups, this was defined amenability for groups already by von Neumann, I think. And so it was already observed a long time ago that amenability of the group is equivalent to nuclearity of its reduced sister algebra. It turns out to be equal the full, and then both algebras are nuclear. And the nuclear sister algebras are those that are very important for operator algebra. So we want to know when a certain sister algebra is nuclear. And the Étale groupoids, they provide models for many of the operator algebras we have, and they generalize in particular discrete groups and group actions. And so it's nice to know when their sister algebras are nuclear, and especially we also get in some cases non-Hausdorff groupoids that model some sister algebras. So it's also nice to know when their sister algebras are nuclear. So it turns out that for non-Hausdorff groupoids, the problem is a bit subtle. So one has to look for some new methods and maybe some new notions also. We need to look at Borel amenability, essential amenability, which is a special sort of amenability related to another sister algebra that we can attach that is different from the reduced one. But we'll see. So this are the main motivation, the questions that we are going to address in this talk. So just a small overview of the history. So about 60 years ago, more or less, Polanyi already proved this result, I guess, for groups. And also together, maybe at the same time, more or less, or 10 years later, Kohns also was looking at von Neumann algebras of groups, and there is also a version for von Neumann algebras relating nuclearity.
Sorry, ALCIDES, I cannot help myself, but I have to mention that Hulanitzky is a very well-known mathematician from my hometown. And he is quite a figure in Wrocław. So yeah, I'm very happy to see him on your slides next to Kohn.
Okay, thank you. And then later, many papers by Claire, Anatole de la Roche, and in collaboration also with Jean Reynaud, they studied also, they have actually a book about amenable groupoids, amenable actions, is mainly about Hausdorff groupoids. They say at some points that some of the results also hold in the Non-Hausdorff case, but you have to be careful. And so actually, yeah, so we are going to see that this Non-Hausdorffness really is brings some problems. So you usually find also some gaps and some problems that the non-Hausdorffness of the groupoid could lead to. And so actually, I think it already appears in the thesis of Renault that for Hausdorff et al. Groupoids, nuclearity of the sister algebra is equivalent to amenability. So this for Hausdorff groupoids is a very well-known fact. So the main point is really here is to look at the non-Hausdorff case. So this is a question that I made myself a long time ago. Is this, so you can also look at the book of Brown-Lazar, and there you can see a proof, so it's elementary proof going directly proving that the sister algebra is nuclear if and only if the groupoid is amenable. And I didn't find similar results for non-Hausdorff groupoids. So this is the motivation, one of the motivations to study and then publish this paper. Okay, so the goals then is to extend the notion of amenability. Essentially, you are going to take the same notion that's already available in the groupoid Hausdorff case, but there are also some issues that we need to address. I'm coming to this point later. And also one of the main points of this paper was also to introduce a new notion of amenability, the so-called essential amenability, that looks at a certain, it's about the nuclearity of a certain quotient of the reduced sister algebra, which is different in general. So this should really be equivalent to nuclearity of that sister algebra. And we also want in general to compare the sister algebras, and maybe amenability should also imply something about the coincidence of the several algebras that we have attached to the groupoid. So, and I already
could you
mentioned.
explain what essential sister algebras are?
Yeah, I'll explain in a minute. So
Later.
just the goals now. I'm going to explain the details in the next slides. So we're going to see that we need, again, I already said this, but we're going to look at Borel functions and so on as alternatives, so to say, to study the amenability. And in the end, we're going to look at certain examples related to recently introduced algebras attached to semi-group actions on groups by Chris Bruce and Xin Li. Okay.
By the way, ALCIDES, if you don't mind me jumping in, when you wrote Bruce Lee, I thought we were making a joke because everybody knows Bruce Lee, the karate champion, Enter the Dragon, and so on. So I really checked that such a paper exists. But these are two mathematicians, so it's much better to say Bruce and Lee. You say Bruce Lee, I think you are joking or something.
Yeah, no, it's funny. Yeah. So it's better maybe to say Xin Lee and Chris Bruce. Indeed, it's a funny thing. I already noticed myself. Okay. So let's go now more into the details of the things. So first, let's just recall topological groupoid is short way to say is a small category with inverses. Going to talk about topological things. So it's essentially a set which has a topology and then a product as a composition of the category, and every arrow has inverses. So we have also an inverse operation, and everything should be continuous, of course. We have especially the source and range maps. I'm going to write them as D and R because S we use for bisections usually. So, and then this is the source or domain map and the range. So, and the main point is of this talk, you only be talking about the Étale groupoids, and those are These are those groupoids where the range and source maps, they are local homeomorphisms. So locally, they are homeomorphisms. On their images, they are always also open. So we allow, as I already said, so the main point is to allow non-Hausdorff topology. But we always assume to build sister algebras local compactness. And I should also emphasize compact here. Sometimes people say compact meaning Hausdorff compact. Here I mean compact, not necessarily Hausdorff, okay? So in the sense of general topology.
Yeah.
Every open cover admits a finite subcover. That's the definition of compact. And the unit space, usually we are going to denote by X. So, and this is always assumed to be Hausdorff at least, okay? So, and since we are going to only look at Étale groupoids, locally the groupoid looks like the unit space. So the groupoid itself is always locally Hausdorff. So, but not globally housed, that's the point. But at least the unit space is nice space. Okay, there are several examples, but just to mention a few, the groups, of course, I already mentioned, they are groupoids. More generally, we can take a group action on a space and form the so-called transformation groupoid of the action. And these, in this case here, they are always Hausdorff. We also have the famous path groupoids of directed graphs that are very important in sister algebra theory. So these are also, by the way, always Hausdorff, though they are nice groupoids. And more generally, we can also take groupoids of germs in the sense of groups or in the sense of inverse semigroup. So an inverse semigroup is a semigroup with a sort of inverse operation. It's like similar to a group, but an inverse in a more general sense. So say we have an action of an inverse semigroup on a space, then we can form the so-called groupoid of germs. It's a sort of transformation groupoid also, but you have to take into account the germ relation. And this germ relation takes into account the structure of the inverse semigroup. So we look at germs which are pairs, S and X, S in the inverse semigroup and X in the space. And this is the equivalence relation. So we say X, Y, S, X is equal to TY, if and only if X is equal to Y. And there is an idempotent, I forgot to say here, this idempotent, the domain, we have the action around. So this common point here, X and Y, should be in the domain. And when we restrict the elements, so to say, or make the product in the inverse semigroup, they coincide with this idempotent. So you should remember the classical germ relation where we restrict functions to a certain neighborhood. So this is generalizing this notion. And since we take equivalence classes here, so it's a quotient space. So usually this is a non-Hausdorff space. So of course, we look at the quotient topology. Essentially. So, but actually we look at a more specific topology where we look at the germs of this form, essentially, where we fix an open subset in the domain of the action starting from S, and then we look at those germs and declare those to be open, and this generates the topology. And this is usually non-Hausdorff. Okay, and this actually, it's a fact that indeed every Étale groupoid is of this form. So this is the general model for Étale groupoids. So in other words, you can think of groupoids as inverse semigroup actions if you want. So it's a then dynamical point of view for groupoid. Okay, good. These are the examples, but we also have the so-called the classical notions of germs. Also, you could take also pseudo groups, which are like semi-groups already of local homeomorphism on the space. And these, so in this case, you get special Étale groupoids, which are the so-called effective groupoids, because it's already represented there by an action on the space. So it's already, the inverse semigroup is already contained in the semigroup of local homeomorphisms. Also, other examples, motivating examples come from foliations, the holonomic groupoids. Usually these are Lie groupoids. We start with a manifold and then a foliation. But in many cases, you can take like a transversal and make this Lie groupoid equivalent to an Étale groupoid. So these sister algebras of foliations, they usually can also be like modeled by Étale groupoids. There are
Can
also
you explain what you mean by Morita equivalence of groupoids?
Yeah, I'm not going to use this, but the Morita equivalence of groupoids is the geometric version of Morita equivalence of sister algebra. So you have two groupoids, and then you have a space of the two groupoids. You have a space where the two groupoids act freely and properly, essentially. So, and then there are certain technical conditions that you need to put, but it's a space with certain actions of both groupoids.
And is it equivalent to having the Morita equivalence in the usual sense of the convolution sister algebras?
Equivalent, I think it's not, but it implies. So if you have Morita equivalence of groupoids, you get Morita equivalence of the sister algebras.
Okay.
There might be equivalence. There might be equivalence in the sister algebras that you don't see in the groupoid level, maybe. But it's essentially the geometric sort of Morita equivalence that you would like to have when you have groupoids. Yeah.
Okay.
Okay, but we are not going to need this, so I didn't give the definition here. So inverse semigroups, yeah, so we can look at them alone and also form sister algebras. So we can look at the universal sister algebras for representations. This would be just C star of the inverse semigroup, or the famous tight versions that were invented by Rui Exel. And these are usually certain these are quotients of the sister S, and they usually recover the algebras that we want maybe in certain situations. And these you can also view, so you attach to the inverse semigroup a certain action on its idempotence, and then you take a spectrum and so on, and then you look at the groupoid of germs of that actions, and these are typically also not Hausdorff. So all these examples here, they are typically non-Hausdorff, lead to non-Hausdorff groupoids. So these are some motivations to look at those groupoids, yeah, non-Hausdorff. So summarizing, so the non-Hausdorff groupoids, they naturally appear in dynamics, foliation, non-commutative geometry. And so one has to be careful because some constructions we have to be more careful, they misbehave. And we need new techniques, maybe new methods, as we are going to see here soon. For instance, to study something about the sister algebras. Like, we need new ideas, so to say. Okay, so let's go more into the details of these algebras, how we attach a sister algebra to an Étale non-Hausdorff groupoid. So we fix from now on, say, an Étale locally compact groupoid, and the unit space is Hausdorff. So the groupoid is locally Hausdorff, so it has a lot of open subsets inside that are Hausdorff. So essentially looking at those, so actually we look at more special ones, the so-called bisections. I'm going to define here in the bottom what's a bisection shortly, but it's an open subset that where the source and the range map are injective, and then they are automatically local, they are homeomorphic on that set. So, and since they are homeomorphic to subsets of the unit space, they are Hausdorff. So, and then we look at spans of, so sums essentially of compactly supported continuous functions on those sets. subsets that are open and Hausdorff, and then we extend, I didn't write here, but we view them as functions on G, extending them by 0 outside U. And this is the point where the continuity breaks then, because the support inside of this U is a nice Hausdorff compact set, but if you look in the groupoid and the global thing, it might not be closed. So if we extend this by 0, you don't necessarily get a continuous function on G. That's the main reason for those elements not being continuous. So as this is the warning here, so the elements here you can view as functions, but they are not continuous globally. So if the groupoid is not Hausdorff, you always have a certain non-continuous functions here. But they can be, by definition, written as finite sums of those functions that are continuous and so on in a certain subset. Okay. This is the space that we attach, and then from there we build a system. Okay, let's pause before we continue to define the system, but let's look at this non-Hausdorffness in a more careful way. So we look at the so-called dangerous arrows or dangerous points of the groupoid. You can look at any topological space. You can look at those points. So these are the points that you cannot separate topologically. So this means that you find a different point in the space where you cannot separate topologically from the other point. So I'm going to give several characterizations about this. One of them is saying just we have a net that converges to these two different points, so to say. So these are the arrows in the groupoid. And whenever the groupoid is not Hausdorff, we always have these dangerous points. And maybe I should also say, even though we have some Hausdorff, like the unit space is Hausdorff inside, we might still have these dangerous points inside the unit space, so that we can also look at the dangerous units. So because we have to look at the global thing. So this is about non-Hausdorff of G. So we just write D for all these points, D for dangerous. And so of course then D is empty if and only if the groupoid is Hausdorff, since we are going to consider non-Hausdorff groupoid. So this D is then always non-empty. So we have these dangerous points around. So
may I have a question?
Yeah.
Sorry. I'm a little bit confused why it is equivalent to being Hausdorff. My impression is that this is something stronger, or maybe weaker. If you have a point which cannot be separated, I would rather think of it like being not satisfying this T0 axiom. Or
No,
maybe
because a topological space is Hausdorff if and only if you have a net, the limit is always unique, right?
yes, that's true.
This is, maybe it was not clear for my definition, but this is what I mean by can be not separated. You can also phrase this in terms of open sets, but this turns out it could be a definition. So we say G is dangerous, a point G is dangerous if and only if you find another point different from G in a net that converges to both.
Okay, I see. Okay, so now it is equivalent. Okay, thank you.
Yeah. Okay, good. Okay, and this subset is not just a subset in the case of groupoid. This topological thing inside there that only uses the topology is actually also a groupoid, is a subgroupoid. It's actually algebraically very nice. So it's an ideal groupoid in the sense that, say, if you have an arrow, the source or the range, the domain on the range of this arrow is also in D. And it's even on leaf. So that's what I said also before. Units can be dangerous. So even though the unit space is Hausdorff. And if you have a unit and an arrow that is at this unit, so you have also a dangerous arrow. Okay, so we can also look at the dangerous units in particular. And so algebraically, this is a nice subset, but topologically, of course, it's very badly behaved in general. So for instance, this here is saying that this unit space of this groupoid is a G invariant set. This is the definition, it's just saying that. And so if the groupoid is minimal, we have no non-trivial invariant subset. So in particular, if the groupoid is non-Hausdorff, this is always dense. So it's might be very badly behaved. Okay, in certain cases, not so badly behaved, but in the interesting case, like the minimal groupoids, this is always dense when the groupoid is not Hausdorff. Okay, let's give a characterization about this. As I said, so these G is dangerous if you can find nets that converge a net that converges to this point and a different point at the same time. It's also equivalent to have a compact neighborhood, even you can choose a compact neighborhood bisection, maybe not open, but you can also choose an open if you want, but maybe now then also not compact, which is in the closed, but not in the closure, but not in the compact set. Yeah. So because the compact, we always find like a subnet that converges this. If you have something in the closure of a compact set and not in the compact set, this must be dangerous. Okay, and so this is also emphasizing the fact that compact sets are not closed, you know, in a non-Hausdorff space. And this is an interesting thing that we found out. So the dangerous points, they are exactly the points where we find one of these functions in this strange CC of G that witness the non-continuity or this discontinuity of this function. So we can, if we have a dangerous point, you can find even an element here and a net that where this function is 0, but in the limit is not 0. So this is explicitly saying that this function is not continuous at this point. So, and this is indeed equivalent. If you have a discontinuity point of some function, the G is dangerous. So in other words, these dangerous points are exactly the discontinuities of functions in this space that we use to build the system. Okay.
And the space is what? Compactly supported functions? What is the space?
This space here, I defined it previously. I think this is the space here. This function here that you write as sums of functions that are continuous in Hausdorff.
On an open bisection. Okay.
Open bisection. You can always look at it.
We just forgot.
Okay. This is the space that we look, and also the space, as I'm going to explain now, that we use to build the system algebras. So this space is not just a space, it's also a nice star algebra. So we can look at the usual convolution product. That's just to take products of the thing that you make products in the groupoid, and then you take those products, is the famous common convolution product. It's possible to prove that this is a well-defined product in this space, associative and so on. And we also have a star operation evolution. That's just, I forgot here. It's of course the inverse here. It's, sorry, it's alarm here now. Maybe just wait a bit for the alarm to go away. Okay, sorry. If you can hear me, okay, now I can continue. So here is a typo, of course, I forgot the inverse here of the group point. And yeah, this is the involution, not just the conjugation. You take into account the inverse operation on the group point, sorry. And then, okay, and then we look at, of course, we want to look at a sister algebra, so we need to look at representations of this star algebra. So, and I just noticing here that since we have functions that are sums of functions supported by sections, we can prove that every representation of this algebra, star algebra, will be in a sense bounded. Bounded mean that you can find a constant, like you can take the supremum norm of these functions, call this C, this doesn't depend on pi, and this then is a bound for all representations that you look. So this in particular says that we can define the maximal sister norm. So this is the first sister algebra that we maybe could look at from the groupoid. So we look at our representations and take this supremum. This is the max sister algebra. We call this the max sister algebra of G. Okay, and this algebra also has a distinguished representation, the so-called regular representation, okay? Yeah. And this is just, again, taking the convolution into account, but we now take convolution of an element here, an element in L2 space of the groupoid, a discrete L2. So we just view this as a set and then look at the discrete. This turns out to make still sense, this convolution in this, for this function. This gives a well-defined representation. And indeed, it's a faithful representation of this algebra. It's an injective map. So in particular, this gives another sister algebra. We can just take the operator norm and define the so-called reduced norm, which it turns out to be also, you can decompose this representation into pieces. Usually this is defined in this way. So you look at the restriction of lambda x to this invariant subspace, which is just the image of the source map. Yeah, okay, this is another sister norm. So we get another sister algebra. This is the so-called reduced sister algebra. Okay, these are very well-known sister algebras that you can attach to sister algebra. Of course, the maximal one maps onto the reduced one by the universal property. So we have, one is a quotient of the other. And also, as I said, so lambda is faithful on CC. So we can also view the reduced as the image inside. So we can view the reduced sister algebra as a concrete sister algebra, and the maximal one, yeah, is some other universal sister algebra. And we, of course, one of the basic questions that already appears, when are those sister algebras equal? Yeah, so this is related to the amenability. Okay, okay, some basic examples just to make it clear that we understand. Maybe for groups, of course, these are the usual group sister algebras that they are defined in the same way, of course. More generally for this, you should have, say, a group action on a space or a nice space, then you get the full sister algebra is the maximal cross product, almost also by the universal property definition. And the reduced sister algebra turns out to also be the corresponding reduced cross product that can be embedded, for instance, in this Hilbert space here. Okay. And similar, the same story here holds for inverse semigroup actions and the corresponding groupoid of germs. So one can prove the same result here for the cross product for the inverse semigroup. Of course, one has to define this correctly, but if you define this correctly, then you get the same decompositions. Okay. Good. This is just to get an idea of how these are defined. And let's now look at another important ingredient for the reduced sister algebra. Okay, on this space, we can look at the restriction map because the unit space is inside G. We can just look at the restriction map. We take a function, we restrict it to the unit space. Okay. We know that the functions here in general are not continuous, and the restrictions also still need not be continuous. But one can prove, it's easy to see that all these functions, they are Borel. And so we can look at these as a map from CC to Borel functions. They are bounded, they vanish at infinity also. Borel functions on X. So if we denote B0X, the commutative, this is a commutative system of all bounded Borel functions from X to the complex numbers vanishing at infinity, it's not difficult to see that this map extends to reduced system algebra. And this indeed gives a faithful expectation. So it's a positive linear contraction that's injective on positive elements. Okay, it's a nice map.
Sorry, can you explain again what is this X?
X is the unit space, sorry.
Unit space, okay.
Yeah, it's the unit space of the groupoid. I fixed this notation, maybe you already forgot, but X for the whole talk, when I say X, X is the unit space of the groupoid. Okay. And by the way, if you take C0X, this always embeds as a C-star subalgebra, sometimes called the diagonal, although it's not a diagonal if the groupoid is not, say, effective and so on. So, but it's a nice subalgebra. And P is the identity there because we just restrict to functions there. But the image lands outside C0. So it's not really a condition expectation in the usual sense of condition expectation. Is what people sometimes call weak condition expectation. You can view Borel functions in the bidual of C0, for instance, and then in this sense, it's a weak condition expectation. Okay, but it's a nice map. That's an important piece for the C-star algebra. And we have another important ingredient here, which is the following. So we have this reduced system algebra is represented via the left regular representation. So we can take, in the L2 space, we can take delta functions like delta of some point G and delta of the source of this point. And then we can look at this inner product. This will be a scalar. And we can just define this number. Yeah, this is like a coefficient. If you view this as a matrix, yeah, this is like one of the entries of the matrix, and then this gives a function. Yeah? So, and you can compute this. It's not difficult. If you start with A in CC, this will be just A of G. Okay, you have to compute something. Of course, you have to take into account the convolution. So this map here, this assignment, it gives you a function, yeah, and it extends the embedding here. So as I already noticed, CC functions are not continuous, but they are always Borel and they vanish at infinity. This is my notation B0G. Yeah? It's a Borel bounded functions vanishing at infinity. So this is already there. And this map here just extends this embedding. Yeah? So it's just a way to view elements of the reduced system algebras as functions. And this is indeed a linear contractive injective map. Okay, but the image of J, this J map, is only in C0G, only if the groupoid is Hausdorff. But in general, we have these Borel functions. Sometimes we just suppress this J map, and we also view C star G as a space of functions. This is the nice thing. So in the reduced system algebra, we can view elements as functions. That's the point. Yeah? And if you view the system algebras as functions, the projection, so the condition expectation is just the restriction map. Okay, good. Some issues about non-Hausdorffness that appeared in the literature. So for instance, if the groupoid is so-called topologically principal, this just means that if you look at isotropy points, the trivial isotropy points, they are dense in the unit space. This is called topologically principal. There's also the principal groupoids that are just no isotropy. And if the groupoid is Hausdorff, it's known that this subalgebra here detects the ideals of the reduced system algebra, meaning that if you have a non-zero ideal, you get a non-zero intersection with C0x. This is an important property that you would like maybe to have for subalgebra, is the ideal intersection property. Okay, but this fails already if G is not Hausdorff, was observed, for instance, by Rui Exel in a paper called Non-Hausdorff Groupoids. So he has a very simple example there. You look at the cross on the plane, and then you look at the reflections around the X and Y axis, and then this is a group of Z mod 2 times Z mod 2, the Klein group, and these, if you look at the germs of this action, you get an Étale non-Hausdorff groupoid that fails to have this property, okay? So this fails in very simple examples. So this is one of the issues that we don't like in the reduced system algebra. There seems to be a problem, and the problem indeed is that this quotient is maybe too large. This is the motivation to introduce this other system algebra. So this is introduced to fix these issues, these ideal issues, for instance. So it's a special quotient of the reduced system algebra. We need to mod out some things in C star, in the reduced system algebra. And what we mod out is the following. So we can look again at this condition expectation that just restrict functions. So I didn't write it here, but this E is essentially the same expectation as before. The only difference is now we look at a quotient of the bounded Borel function, say. This is the ideal that we mod out. We look at the ideal in the bounded Borel functions on X. We look at the ideal of functions with meager support. Meager is a countable union of nowhere dense sets, sets that have empty interior after you take the closure. So you take those, these are sort of small sets in general. So you mod out the functions that are supported in a meager set, so to say. And then you mod out the expectation, and then this is a new expectation, but because you go into a quotient, and then there is a quotient. This is not faithful anymore because you look into a quotient on this reduced system algebra, but you can make it faithful by taking a quotient of the reduced, okay? Indeed, there is a unique quotient that factors this map into a faithful condition expectation. I'm just writing here as turns out to be the so-called local multiplier algebra of C naught of X, but this is not very important. Just look at this definition here, okay? Okay, and it's important to know what are your quotient out? What are the elements that are killed by this quotient map? Yeah? So this is, let's call these elements singular, or let's call this ideal the singular ideal. Okay, so here's a nice description of this ideal. Was already observed, I think, by other people, but in this general form, I also prove a sort of version of this in the paper for CC functions. But here is a very nice result by Bartosz Kawaniecki and Ralf Meyer. Recently proved the following: the singular ideal is exactly, if we look at elements of the reduced system algebra as functions, these are just the elements that if you look at A star A, and restrict to X, this is meager in X. So essentially this, the definition, so the definition of the condition expectation essentially is asking for this because you look at the quotient and this turns out to be exactly the ideal that you get, okay? Moreover, if the groupoid is, say, second countable or sigma compact, or more generally, if it's covered by countably many bisections, and this is really necessary for this characterization, then we can say even more that this singular ideal is just the space of, is the ideal of functions with meager support. Yeah? And this is also, moreover, equal to the functions that have compact, that have support inside D. D are the dangerous arrows. Yeah? And we can also look at dangerous units just by looking at this product and then restricting to the unit, okay? This is a very nice, so what we are modeling out are just the functions that have support containing D. Okay, and by the way, this D is in general might not be meager, but here's the reason for why this works in the second countable when G is covered by countably many bisections that I'm just calling SNs, then you can easily see that D must be contained in this union. And this union is one of the basic examples of a meager set. Okay, so in this case, you see that D is meager and then this previous result works. Okay, now we are going to focus exactly at functions supported on D, so to say, or outside D. So this is the point. So we can say, for instance, a representation is essential, or the representation of the groupoid, yeah? So a representation of the sister algebra of the groupoid, we can say is essential if it is supported, if it vanishes on functions that are supported on these, say. Yeah? So we can look at this definition. And there is another sister algebra that we can attach that was not introduced before. We wanted to introduce it in this paper, but it's a very natural companion, say, of the essential sister algebra, but it's a maximal version. So we look at the, essentially we can view this in two ways. It's the maximal sister algebra for essential representations, or in other words, we can first look at the space of functions modeled by the singular ideal inside there. So the functions with support in D, this is an ideal, and then you can look at the universal sister algebra of that quotient. This turns out to be the same. So this is what we call the essential max sister algebra. Okay?
Thank you.
Okay, good. And by the way, all these algebras that we have, they are quotients of the maximal sister algebra. And this essential max is exactly the quotient by the max singular ideal. So you just take the algebraic singular ideal and you closed in the max norm, and then you get an ideal in the max sister. This is the quotient that we look at. Okay, here's a nice regular, nice representation of this essential sister algebra. So we look at the regular representation of this, can be viewed as a representation of the max sister algebra, and also a representation of CC. And then we sort of restrict this representation to a subspace. This is an invariant subspace because D is a subgroupoid. So we can restrict the representation to this, say, subspace of L2, and this gives a sort of sub-representation. And then this representation is essential. And moreover, it extends to a faithful representation of the essential representation. In other words, the essential sister algebra is embedded as a space, a sister algebra of operators on this L2 space here. So, Okay, we just cut essentially the functions support on D and just remain with the rest essentially. Okay, let's look at some example. The basic example that we have to test some sort of our results is this toy example here. So we take a discrete group and we take, say it's countable group and say X is the unit interval, 0, 1. Very basic. You could also take other spaces here, but that's just to take the unit interval. And we look at the group, but we add a 0 to the group, a formal 0. And this then replaces the group by an inverse semi-group with 0. Yeah. And then we look at a very, very trivial action of this semi-group or the group. We look, the group acts trivially on X. Yeah, so we acts trivially, the identity of X. But the 0 acts by the identity of the semi-open interval 0, 1. Okay? And then we take the groupoid of germs as usual, as described before. And this groupoid of germs turns to be just as a set, since the action is essentially trivial, is just this interval here, and then this joint union with the group. Okay, you can compute, it's not that very difficult. This is as a set. As a group, or as a groupoid, it's a group bundle. So I'll put a picture in the next slide, but it's a group bundle where we have just the unit interval as a base, and you add in the endpoint, at the endpoint 1, you add the group as an isotropy, okay? But the topology...
So this unit interval X will be the space of units of your groupoid, right?
Say again, sorry?
So this unit interval X will be now the space of units of your groupoid, right?
Yeah, X is always the unit, yeah. Yeah, this will be the unit space, and it's a group bundle where, so I have the picture here. So you view this groupoid as this. So you have the unit interval here, 0, 1, and you view the group as in this endpoint we attach the group in these vertical points here. Gamma 1, say the group is countable. And you view also the 1, you could view the 1 as the unit of the group. Yeah, so and this is the group bundle, the sort of trivial group bundle, except at this endpoint it has gamma as the isotropy group. Okay, the unit space carries the usual topology. And maybe I could also say here the closed unit interval is contained in G, and there we have a nice Hausdorff topology. But when you approach 1, so if you have a sequence like this here, these dot points here converging to 1, they will converge at the same time to all these gammas, the elements of gamma, okay? This is the topology of this groupoid. Okay, let's now look at this space for this groupoid. Of course, the dangerous points are exactly the elements of the group. We make all the elements of the group dangerous, so to say. And the space of functions, it's not difficult to see. You write the functions as a sum and blah, blah, blah. And then you see that there is a limit for t converging to 1. And this limit will be a sum of the values of the function at elements of gamma. And this sum must be finite so that the function has compact support. Yeah? So these are the functions. We just take functions on the groupoid that are continuous on this open interval, and the limit at 1 is this. You see, it's not a continuous function in general because it has these values. So indeed, if you use this description, easily follows that the maximal system algebra is just a subalgebra of the direct sum, where we take C01 as functions A, and B elements in the full sister algebra for which there is a matching condition. So the value at 1 is equal to the value of the trivial representation, which is essentially this here on the group. And this is the maximal sister algebra. Okay. If the group is amenable, the full and the reduced coincide. So they are this algebra. Otherwise, if the group is not amenable, then you don't see the trivial representation in the reduced sister algebra of the group, and then the reduced sister algebra is just the direct sum. Okay, so you see it's different. And let's look also at the essential sister algebra. So essentially, so in the essential algebra, in this algebraic essential thing, already consists of just continuous functions on the unit interval. So you essentially mod out all these singularities here, because these are the dangerous points. So you get a very trivial thing in a sense here. So it's a commutative sister algebra in this case. So you see it's also very different, yeah? So the nature here is non-commutative. In general, here is a commutative. We also see in this example, and this is one of the motivations, so the essential sister algebra can be nuclear, like even commutative, and the reduced or full sister algebras might not be nuclear. Yeah? So that's the main question that we want to address also. When exactly are these quotients nuclear, for instance? Okay, let's look at Borel algebras. Yeah? So already in the beginning, I already observed that all these functions, they are not continuous, but they are always Borel measurable. They are also bounded, they vanish at infinity, and so on. So it's natural to look at these as a subspace of all bounded Borel functions. We can also take compactly supported. Let's look at this, okay? This space that we look to build the sister algebra is a subspace here. Yeah, so we can look at this space. And the nice thing is all the things that we define, including convolution, the involution, all these representations and everything makes still sense on this larger space. Okay, so summarizing, we can define essentially the same things for this larger space. So we can define a maximal sister algebra. We can use the regular representation, extends to this. We can define the reduced sister algebra. We can still look at functions supported on D, and then we can define a certain maximal essential quotient, and we can also look at the essential Borel sister algebra. So the reduced sister algebra will be, by definition, a subalgebra of this, and this will be also a subalgebra of bounded operators on L2. And the essential sister algebra will be a subalgebra of this. So we just enlarge, take Borel functions and view everything either in L2 of G or L2 of G minus D. Okay? So we do exactly the same. Okay, and here is a nice thing. So, of course, if we want to now go between C star and Borel sister algebras, it would be nice to have a control on the representations, yeah, of both algebras. And this is a nice theorem. So we can prove that every representation of CC extends canonically to Borel, to this space, this algebra. It's not difficult to prove this. So we know that every measure on CC we can extend to Borel functions. So we just look at representation and we look at coefficients of these representations. These will provide you measures, and then you extend the measures, and then you will use these measures to extend the representation. It's a very canonical extension.
Sorry, could you explain again? Could you explain again what you mean by Borel sister algebras?
So you look at the space again here. Look at the space of compactly supported Borel bounded functions.
Okay.
Okay, and then you notice that the same operations, convolution and involution of defining CC, they still make sense. And not only that, the representations, they all extend. In particular, the left regular representation extends, so we can play the same game and define all these versions. They are large algebras in a sense, but the advantage
But they are
of
still
this,
sister algebras.
they are sister algebras. Yeah, all these here are sister algebras. Like the big sister algebra is this. This is a bit smaller, and then we have the essential quotient and the max essential quotient. So we have a commutative diagram of sister algebra, and I could complete this to a cube. Yeah, so I attach here the sister algebras in the other face, and there are natural maps between them. So we have at the moment, I think, 8 sister algebras.
Wow.
Okay. And this is one nice relation about them.
Sorry, may I also ask a question about the previous slide?
Yeah.
I wanted to ask because previously the construction of the essential sister algebra was based on this expectation which took the functions vanishing at infinity on the space of units. And you've said that this space was taken not into the space of continuous functions, but Borel functions vanishing at infinity. And now, what are the differences in this construction? You jump from the Borel compactly supported functions on G to Borel vanishing at infinity functions on X, and then have the same expectation, or there is something different?
So of course here this here is even better because we can just restrict any function again to the unit space, and if you restrict a Borel measurable function, it's still Borel measurable.
Sure.
So actually in this algebra here, we do have a conditional expectation onto the Borel bounded vanishing at infinity functions on G on the X on the unit space.
Okay, so
in
this case, it is truly an expectation because it has and the ideal by which you divide is the same as in the case of continuous functions, right?
It's the same, exactly the same.
Okay, great. Thank you very much.
Just that we now look at more functions. That's the only difference. And then we don't care, maybe they are not continuous, but they were not continuous before, so this is natural to consider, right? So, and the point here is that if we look at the techniques that you use to prove many things for continuous functions, usually use partitions of unit, right? Partitions of unit only exist if you have like a Hausdorff locally compact space, and must be paracompact even, yeah. But if you are not Hausdorff, then you don't have partitions of unit. But if you look at Borel functions, you can just partition the support of the function into Borel sets, and then you have a sort of partition, not just partition of unit. Yeah? And this is the main ingredient that we use here to build approximations and so on, and arguments. And the nice thing is, I was saying, every representation naturally extends, and moreover, not just extends, it extends in a way that preserves commutants or bicommutants. It's the same. So the bicommutant, the von Neumann algebras inside here, they will be the same. If you look at von Neumann algebras, you see no difference. Yeah. So it's a sort of von Neumann algebra, this Borel sister algebra, but it's not really a von Neumann algebra, right? So I think it might be in some cases a double star algebra, but even that is not true. But it's in between a sister algebra and a von Neumann algebra. It's a large sister algebra. So as a consequence of this theorem here, in particular, we get an embedding. Yeah? Sister algebra max embeds in the max Borel sister algebra, naturally. And moreover, since this preserves the commutants, you can prove even more this embedding remains an embedding after you take any tensor product, like the maximal tensor product. If you look at the maximal tensor product with any other sister algebra, this remains an embedding. This is a result by the way, for instance, in the book of Brown-Zhao, is max injectivity is essentially characterized by existence of a certain maps that preserve commutant or go into by a commutant. Anyway, so in particular, this says also already here, since this preserves injectivity of max tensor product, nuclearity of the max Borel sister algebra already implies nuclearity of the subalgebra. This is not true in general. A subalgebra of a nuclear sister algebra is only exact, right? But in this case, it must be nuclear if the big algebra is nuclear. Okay, good. Here we have an open question. So in the first version of our paper, we had this assertion for also a version for essential representations, but we found a gap in the proof, or actually it was pointed out by Xin Li to us. There is a gap in the proof, so we cannot prove, and indeed it's not true, that if you start with essential representation, this extension will not be essential in the sense that it vanishes on the ideal of functions supported on these. Yeah. For example, the trouble is you may have that reduced and essential are the same, even though the groupoid is not Hausdorff. This is a weird thing that might happen in some cases. Yeah. So the coincidence of this algebra is actually a big question that people are trying to understand, but it might happen, was already observed by many people, that it might happen that these algebras coincide. And if this is the case, then every representation is essential. In particular, this lambda x for x in D, they will be essential representation, but these representations, they do not vanish on this large idea of how functions we support containing D. For instance, you can take the characteristic function of this point. Okay, this is really a problem that we were not able to fix. So we have a big question here that will have influence on our main results. So this is the question we have. It's not clear to us, even though it's true that not every representation extends to essential. We still have a map, and we still have a homomorphism from the essential max to the essential Borel max by universal properties, but we don't know whether this map is injective, this representation. It could be, we don't have any example. Yeah? But actually what we really would like to have is max injectivity to prove the same. Yeah.
I mean, have you thought about looking at these things with a twist on the groupoid, because the twist may affect the coincidence between the essential and the reduced sister algebra.
No, we didn't look at these yet, but we maybe plan to do it in the future.
Because I mean, I suppose you know that if there are instances in which the reduced in the sister algebra, the reduced in the essential algebra.
Hello?
It seems that Rui has frozen.
Yeah, exactly. I couldn't follow.
Yeah, now, Rui, you were frozen for a while. Could you please repeat what you were saying?
Okay, so what I'm saying is that the equality between the reduced sister algebra and the essential sister algebra depends not only on the groupoid, but also on a possible twists that you put on the groupoid.
I remember you have an example where this depends. Right. Well, we didn't look. The answer is we didn't look yet at twists. it could be revealing to look at those and maybe we find something out. But yeah, we plan to do this maybe in the future. And I believe that most of the techniques that we have here will work also for twists or even fell bundles over groupoids. But we didn't yet think about the details.
Okay, thank you.
We have a paper. We actually have a project that goes in this direction to analyze similar things for fell bundles. They are fell bundles of a groupoid. Okay, but thank you, Rui. Let's continue. So let's look now at really the main question. So the main question that we want to address here is about nuclearity of all these algebras that we have. Yeah? So when exactly is the max sister algebra nuclear, the reduced, the max Borel? We can now look at the reduced Borel sister algebra. Also the essential versions, we can make the same questions. Yeah, so we are going to give answers for these questions in terms of amenability. Yeah, so just recalling quickly, I have been talking about nuclearity, but now let's review the notion of nuclearity just to refresh our memories. So we can say a sister algebra is nuclear if the identity map is can be approximated pointwise in norm by finite dimensional CCP map, so to say. More precisely, we find CCP map that go from the algebra to matrices of finite dimension and the other way around. CCP maps mean completely positive contractive, and when you take the composition, you approximate the identity pointwise in norm. And it was it's a well-known result that this is equivalent to coincidence of max and minimal tensor products with any other sister algebra. This is result by mainly, I think, by Lenz, Kirchberg, and Choi-Efros. Okay, so we are going to use both properties of nuclearity. We use both in the proof. Okay, let's now go to...
Could you please go back to the previous slide?
Yeah.
As I'm sure you are aware, there is this concept of nuclear dimension, right? And every sister algebra finite nuclear dimension is necessarily nuclear, but I guess not the other way around. So there is, and the definition of a nuclear dimension is very similar to this definition of nuclearity we just presented. And I'm asking my question right now because now people can stare at this definition of nuclearity and somehow think about the definition of nuclear dimension. And I was wondering if in your considerations where you emphasize nuclearity so strongly, will you have this nuclear dimension popping out somehow or not at all?
Eventually in the future, maybe, but we don't have plans at the moment to look at this question. I think there are results, I think, for when a Hausdorff groupoid sister algebra has finite nuclear dimension. I think there are some results, but I'm not sure. Yeah, so probably some of these results also extend to non-Hausdorff, but yeah, it's always an extra work usually to do it for non-Hausdorff groupoids. We don't have plans at the moment, but it's an important question indeed. You are right. At some point, it should be looked at.
Because, for commutative sister algebras, it has a clear meaning. This is the covering dimension. So it's always interesting to see what it means in other geometric settings.
I think there are many questions still. I am not an expert, so I'm far from knowing much about this finite nuclear dimension. But I think there are results. But I think even for classical cross products, there are questions, I think.
Yeah.
Okay, good.
Okay, thank you.
Yeah. Oh, okay. So let's look at Borel amenability and topological amenability as well. So the idea that we use for amenability is in terms of positive type functions. Yeah? These are used in the group case, for instance. So what is a positive type function? So it's essentially a function which is a positive convolution of this form. So in the algebra, now we can look at either at a CC function, or we could look at a Borel function. Why not? So, but this is our prototypes of positive type functions. Yeah? And these functions, they are used to produce CCP maps. Yeah. So, and then if you have a net approximating, say, the identity or the unit here, you will have some approximation on the system algebra. So the main point is that these maps, they induce naturally, I am going to talk about these maps on the system algebras. Okay. And how are these maps defined? So it's very simple. So you take one of these functions and you just multiply them by another function. Multiply now here means pointwise product, not a convolution. Yeah. So we just take this function and we pointwise multiply. This is a different structure. Okay. There is a simple problem that we also didn't notice in the first version. It was another small gap that we had, but this we could fix. So this space here, another strange feature is that it's not closed under pointwise multiplication. It's very easy to see even in this snake with many heads that we have. If you multiply two of those functions pointwise, you will produce a function that's not in the same space. So this map is not well defined in this level, but it is on Borel functions. That's one of the reasons why we need to look at Borel functions if we want to approach amenability or nuclearity via these multipliers. And that's why we need to look at Borel functions. Okay, but this is not a big deal. So we can look at Borel functions. This is the solution. Or we could also look, and we use this, we could look at the algebra inside the Borel functions generated by functions in CC. We just call this an auxiliary algebra or space. Is bigger than CC, but is still close. So if the groupoid is Hausdorff, this would be just CC, but otherwise this is eventually bigger. Okay, so then we are ready for the definition of amenability. So we say the groupoid is Borel amenable if there is a net of functions, say in the Borel space of functions here, which is sort of bounded in a certain suitable norm. So you take a sort of L2 norm here in the direction of the fibers, and in direction of space, you take the subnorm. And then the main point is that these functions, they converge pointwise to 1. Why? Because
sorry. Just one clarification. G here is any groupoid or Étale groupoid?
Étale, always Étale.
Étale.
But this would also make sense for any other Borel groupoid even. And this definition already appears actually in another slightly different form in the papers of Renaud and Claire. Yeah, so they talk about Borel groupoids and so on. So yeah, using Borel structure, but we only look at topological Étale groupoid. Okay. And then that's the point. So we need an approximation of the unit, pointwise approximation. But of course, we need to have some control on the norm, and this should also converge on compact sets uniformly. That's the thing. So we have essentially a net of positive type functions with compact support that converge to 1 nicely, pointwise. And if we can take, our first definition was if we can take psi I in CC, we say is topologically amenable, but that due to the fact that this is not closed under pointwise multiplication, this is actually too strong. So we allow now functions in this auxiliary algebra or auxiliary space. And then we say it's topologically amenable. Okay. Similarly, we say the groupoid is essentially amenable if we can do the same, but only outside D, so to say. So we have seen that the essential algebras, they are related to functions that are as a quotient of functions by the ideal of functions that have support inside D. So we should look only outside D. This is the idea. So Borel essentially amenable means that we found a net in the same thing, the same way as before, but now only the supremum outside D, and the supremum also only outside D uniformly goes to 1 only outside D, but on compacts of G. So it's a bit of a mixture, because this space G minus D might be very bad. Yeah. So this might be dense, so there might be not too many compact sets there. So we should look at compact sets in G, but we only look at approximations outside D. Okay, this is the idea, and the topological essential amenability is the same, except that we now look at this smaller subspace. Okay, and this is one of the main technical lemmas. So if we have one of these functions, as I already said, they induce functions on Borel space just by pointwise multiplication. And indeed, one can prove that they extend to the maximal Borel completion. They give you CCP maps if the norm, the L2 norm is at most 1. They are contractive and completely positive. So you prove this essentially by proving that these maps on the algebraic level are algebraically positive. So it's a computation, and at this point is where we use partitions of unit and things like this. So, and that's the big advantage of looking at Borel functions. We now can just partition the support of the functions and do the computations on bisections, essentially. That's the big advantage. And then looking at the regular representation, we can also see that these maps will be bounded for the reduced norm. So they also extend to this. We can also prove versions of this for the essential norm, essential algebras. There is no problem at this point. So you can see if there is amenability, we will get these maps here, they will approximate the identity. And another point is that if you have a compact set, if this is a compactly supported function, the image of these maps, they will be in a nice subspace, will be always contained in the space of functions with a fixed support inside as a fixed compact set. So this is used to control the norms and prove that all these norms are the same. Okay, indeed, this is the main result. So the groupoid Étale is topologically amenable if and only if it's Borel amenable, if and only if the Borel system algebra is nuclear, if and only if the reduced system algebra is nuclear. And in this case, we have the weak containment properties. The Borel max is equal to the Borel reduced, and the C star max is equal to the C star reduced. So we have a nice thing, and this turns out to be our equivalent. Okay. Okay, in this, we would like to have the similar result for the essential algebras, but due to this previous problem that I mentioned, we could not prove yet the same result. What we can prove, at least, is this. So the essential version of this theorem is Borel essentially amenable is equivalent to nuclearity of the Borel essential system algebra. And in this case, the Borel essential max and the Borel essential do coincide. We can prove also that nuclearity in general of the essential system algebra implies topological essential amenability. But we don't know about the converse in general. So the problem is this previous problem that I mentioned. We don't know whether this is max injective. So if this is max injective, then the converse holds. And then we have the complete analog for the essential system algebra. Okay.
Sorry, what does it mean, max injective?
Yeah, max injective is injective and is still injective after you tensor, max tensor with any other system algebras.
Okay, thank you.
Yeah. Okay, let's quickly say some quick applications. So one of the motivations were this Chris Brew and Shelley semi-group algebras. Let's talk quickly about this. So these are algebras that you attach to semi-group, not inverse semi-groups here. They are left cancellative, say countable monoids. So you say this is a sub-semi group of a group, say, and then you might have this semi-group acting on a group by homomorphisms, yeah, by injective homomorphisms. So this is what they call algebraic action. So you could have a set of endomorphisms of the group that are injective, say. And then you can use L2 of the group and these endomorphisms to build isometry if the maps are injective, and then you build a sister algebra inside here. This is a natural sister algebra you can attach to this situation. It turns out that you have a groupoid model for these algebras. They already described. So one can also look at a certain inverse semi-group and then a certain boundary and then build a certain groupoid. It's not so important for us here. It's just the fact that there is this nice class of sister algebras. And what we could prove, that this was one of the main motivations, that they observed that this sister algebra, of course, it's a quotient of the max sister algebra of the groupoid. I think it was not clear that this lies maybe lies maybe between the max and the reduced. I think it's not true indeed. So what we could prove is that this algebra naturally sits in between the max essential and the essential. Okay, and we wanted to know when is this sister algebra nuclear, say. Yeah? So we were expecting to prove that sister nuclearity is essential amenability of this groupoid, but now we cannot prove the full result. So what we can prove is that nuclearity of this sister algebra implies at least essential amenability by this general result. We believe the converse is true, but we are not able to prove this at this stage. Okay, so we only have a partial result, unfortunately, in this respect. But there is another funny thing here that I found interesting. Even for classical cross products, our results say something interesting. Let's say we have a classical group action on a space. So gamma is a discrete group, and we have a nice space, and we have then the action and the transformation group point. Okay, this is Hausdorff. Everything here in this case is Hausdorff. Yeah. But our main result about the usual sister algebra says the following. So this part here was already known, but also follows from our result. So the cross product is the sister algebra. It would be either the full or the reduced. The transformation groupoid is the groupoid. And this was proved in other works by Claire, that this is also amenability of this groupoid is equivalent to amenability of the action in a certain sense. What our result says, and this I think it was not true or was not observed before, is that this is also equivalent to the nuclearity of this Borel sister algebra. And the Borel sister algebra is just that, the cross product, you take the cross product, either full or the reduced, on the action induced on Borel functions vanishing at infinity, yeah, and bounded. Okay, here's is the what indicates that this is on the border of maybe not being true. We cannot replace this by the space of all bounded Borel functions. Even if we take just a set, a discrete space, we can take, for instance, gamma here, and then if we take all bounded functions, so what happens is, if the group is exact but not amenable, then this algebra will be nuclear, but the other one will not be nuclear, so to say, or the other one way around maybe. Yeah, so I'm a bit confused here, but this result does not extend if you replace here by all bounded Borel functions. It's important to take this zero here. Yeah. We can also not replace this by L infinity of X by similar reasons. So we can take even a compact set here, compact space. We could take any free action of an exact group. This will always be nuclear. Yeah. So, but the action, the groupoid is not amenable. Yeah, exactly. Okay, so but this follows from our results. But you must be careful here to take B0X and not all bounded Borel functions. So just to finish, so a summary, so amenability, we still prove that is equivalent to nuclearity even for non-Hausdorff groupoids. We look at essential amenability, but we found some subtleties appear there. But we tried to prove the same results, still not complete. So our methods say that it's nice to look at these Borel algebras, Borel functions, and so on. This might also have applications for other concepts, and we have some applications. And some future possible works could be like complete this essential thing that's missing, and maybe look at functoriality. This is one of another problem of these essential algebras. They might not be functorial. This is some of the things that one should maybe study, and maybe extension of these results to other concepts, maybe non-Étale groupoids and so on. So thank you. This is the end.
Muito obrigado.
I think it was exactly on time.
Perfect timing. I mean, you finished your talk within 30 seconds. I mean, this is really high-end precision, you know.
Okay.
To speak for exactly 90 minutes and say 25 seconds, that's impressive. Okay, let's have further questions. Anybody? Diego, Adam, Rui, go ahead.
I have a question.
Oh, Jeets, hello. Yes.
Hello. I'm not sure if it's a coincidence of the example, but is it possible that maybe the essential sister algebra of a non-Hausdorff groupoid is the reduced sister algebra of a Hausdorff groupoid?
It could be. I forgot to mention there is a recent paper that also has some intersection with our results by Xin Li, Kevin Briggs, right, and other people. I think 4 authors. They study what they call covers of non-Hausdorff groupoids. So it's possible, and we had indeed this idea at some point also to use this groupoid. There is this felt topology that one can use in the closed subspace of a non-Hausdorff space to produce a Hausdorff space. So there is a nice Hausdorff groupoid when can attach to a non-Hausdorff groupoid, and they prove, I think they don't prove what you suggest could be true, but they prove, for instance, that nuclearity of this reduced sister algebra of this groupoid is maybe implies or something like this. So it could be true, maybe that the essential sister algebra is maybe the reduced sister algebra of a Hausdorff groupoid. Yeah, this could be happening. I don't know, but it's probably related to these covers that they have. I would look at this.
So if I may say something, it can happen, but it cannot happen at the groupoid level. So if it happens, the diagonals of algebras, the commutatives of algebras of the unit spaces cannot be you cannot send one onto the other. So it has to be. So if it happens, it is a matter of sister algebras, not of like groupoids.
Right. Yeah, the groupoid is always different, but it could be that the essential sister algebra is related somehow to the reduced sister algebra of the larger groupoid. I think they prove, right, Diego, that they have some results about like if you look at this Hausdorffization groupoid, we also looked at this and we also thought that it could be true, and they indeed prove it. So the nuclearity of these Hausdorff Groupoid system algebra is indeed equivalent to nuclearity of the non-Hausdorff Groupoid system algebra. But they also have problems when they look at the essential. They only can prove one direction.
Yes. Yes. So
Nuclearity, yeah.
So they can only prove from the essential you get from the essential being nuclear you get some kind of amenability, essential amenability, but not the other way around. Yeah.
Exactly. So they have essentially the same problem. Maybe it's not true. So we were not able to prove the converse.
But at least in the example of the snake of several heads, the unit space was the same for the groupoid and this kind of Hausdorff applications.
No, it's not the same. You also change the unit space. This is one
was
point.
It is just a continuous function on 0, 1, where you take the essential algebra?
If you take this example that I had in the slide, you mean what happens there?
Maybe I remember incorrectly, but from what I remember, if you take the essential algebra, it was just a continuous function on 0, 1.
Yeah, this is the just in this case our result holds, so the converse holds in this case. It's no problem. We were basing we tested everything in this example. So in this example there is no problem, but in this example is sort of a simplified example. It has the issues of non-Hausdorffness, but for instance the danger sets are closed in this case. Yeah, so it's a special example. It would be nice to look at minimal examples where this dangerous units or dangerous set is dense, and this is where we don't know. Yeah. But this unit space indeed changes. If you look at this Hausdorffization, indeed what changes essentially is only the unit space. So you essentially this unit space of this Hausdorffization is the image. You take the condition expectation and you take, I think, the image and the spectrum of the system algebra generated by the image in the Borel functions, and then you get some commutative space, and this will be the unit space. And the original groupoid still acts there, and then you take some sort of transformation groupoid.
May I ask a question?
Go ahead.
So, I mean, you may be kickstarting a whole set of other projects. Like, for instance, when you look at this Borel algebra for, say, a Hausdorff Étale groupoid, can you tell when is this algebra simple?
Oh, good question.
I mean, like everything that people have been doing for usual groupoids, now you have similar versions to this.
I think they don't share the same simplicity of because you could, like, you will produce some ideas, I guess, right? If you just take, no, in this case it's not, but you might be getting new ideas in this Borel algebra, so it could be, I think simplicity will be something stronger, but I don't know. Yeah, we didn't think about this.
Another big question would be, like you in the standard case, you know that the representations of the groupoid algebra corresponds to representations of the groupoid via this Renault disintegration theorem. So if you have a representation of the Borel algebra, can you understand this in terms of some sort of a representation of the groupoid?
Another good question. Yeah. So we certainly have more representations, and looks like these will also hold like a disintegration theorem for representation. I don't know also, we didn't think about this, but I believe that if you look at Borel algebras, we have some facility like in understanding maybe some steps of the disintegration, because this is the main point here, right? So we can break the functions, partition, and so on. So this I think it's a very natural place to look at the representation, this integration. I think it will have many applications, but indeed, so you are right. So there are many questions that one can now ask about these Borel algebras. So it was for us just a device to prove something about the sister algebras, but indeed it's maybe it should be studied in its own right? So these algebras, they should be studied maybe, and yeah, results like this, what you were asking, but we didn't think about this.
Okay, thank you.
Anybody else?
Can I ask a quick question?
Of course.
Thanks for the lovely talk, ALCIDES, first of all. I had a slightly niche question, I guess. You mentioned this result characterizing the singular ideal in terms of the support of like the expectation of A star A having meager support on the unit space.
Yeah.
And this one from Bartosz. And then you mentioned the case if your groupoid is covered by countably many bisections, and you get like nicer, more checkable conditions. Did you end up having to restrict at any point to that setting for your results so that you had to actually use that characterization?
Maybe I was not clear, but at some point in the slide, I said from now on, let's assume that the groupoid
okay.
is forward. Yeah, so in our results, actually, we assume in the main results, we always assume the groupoid is countably covered by bisections.
Okay. So the reason I bring that up is because the result is more generally true. You don't need the covered by countable bisections condition. What you can do, you do this by
the result. Okay.
What you can do is you take the elements that you want to of the reduced C-star algebra that you want to check whether it's in the ideal. You look at its support as a function on the groupoid via the J-map, and this has to be contained in countably many open bisections.
Okay.
And then you take the open subgroupoid with full unit space of the original groupoid that is generated by these bisections covering the support. This is now an open subgroupoid which is covered by countably many open bisections.
Okay.
And something the function will lie in the singular ideal for the bigger groupoid C-star algebra if and only if it lies in the singular ideal for this open subgroupoid.
Okay.
So you could do everything on a kind of countably generated or countably covered subgroupoid that contains the support.
Then probably we can, using this more refined technique, maybe improve our results to also cover the general case. So I should also say that this result about representations, extensions to Borel algebras, there we also use, because at some point we need to deal with a measure, and then we need some countability assumption. But Xin Li and the co-authors, they indeed prove that this is not necessary. They reprove this result in full generality.
Okay.
But this is a small point, but this is what you are mentioning, maybe more interesting. Maybe we can probably, I believe it's not really necessary, this assumption. It's just more comfortable to work with, and then we don't have these technical assumptions. And of course, I should also say that this assumption is very mild. It's not
of course.
so strong. So sigma compact, I believe it's very close to sigma compact, but we don't know also an example. Sigma compact implies this. I'm not sure whether this assumption on having countably many open bisections.
No, because you could have a group action on by a countable group on a very large topological space, and the transformation groupoid may be too big then, because the individual space might not be sigma countable.
You can even take the trivial group.
Oh yeah.
No. Okay, right. Yeah. Right. Okay. The trivial group. Right.
Yeah.
Okay. Right.
And
I think we mentioned this in okay. Yeah, it's clear. Okay. Yeah. Okay.
But it's a kind of like second countable up to the unit space.
Yeah. Exactly. The dynamics is countable. Yeah. The inverse of my group part. Yeah.
All right, but thanks very much.
Thank you.
Diego, did you want to weigh in? I saw you unmuting for a while.
No, I think I disagree with what Alcides said. So the method that you mentioned, Jono, so if you have an element in the reduced hysteralgebra and you suppose that it's in the kernel of the quotient map onto the essential, so it is true that you can construct an open subgroupoid that is covered by countably many open bisections for which this you can work with. But the point is that these you can do only for like one-on-one, so one-by-one elements in the reduced hysteralgebra. You cannot do it for all of them at the same time. And the point of the theorem is actually, I mean, the thing is that the theorem of Bartos and Ralph, so I think Bartos and Ralph, what they prove is that the kernel of the quotient map is all the elements whose support. So if you take A star A and then you take the condition expectation of this, then that has meager support. But then the one of the points of the project with Alcides is that this is equivalent to having the support being contained in D, in the dangerous units. And this is only true if, this is only true for all of them at the same time if, this is only meaningful if the groupoid can be covered by countably many open bisections. Because if you need uncountably many open bisections to cover the groupoid, then the dangerous unit may as well be all of it.
Okay, so I agree with you there. It's not so the correct statement, and what I meant to say is that an element of the C-star algebra of the reduced C-star algebra belongs to the singular ideal if and only if it has meager support. Not that its support is contained in the dangerous points. That would not be correct.
Yeah, exactly. This is true in general, but
obviously every unit could be dangerous if you have a non-second countable or non-countably covered thing.
Yes.
So our definition of essential amenability in general maybe should account for this difference. So maybe it should be a more complicated thing, looking at approximations outside meager sets and things like this. So we can only look at this outside D or inside D in this situation. Otherwise, we need to look at more general meager sets.
Can you remind me what a meager set is?
The countable union of nowhere dense sets, and nowhere dense is a set for which the closure has empty interior.
Something like the boundary of an open set is always nowhere dense.
Basic example is the boundary of an open set.
I think the idea in this case, like for these functions, you take one of these functions that's supported and continuous on an open bisection. The only place where the discontinuities can occur ends up being at they occur at the boundary of this set or in part of the boundary of this set. And so when you then take countable sums of these for your span closure in the reduced C-star algebra, you then have to take countable unions of these boundaries.
How we prove this, one of these results. Yeah, exactly. Thank you, Jonathan.
Okay. Anybody else? I'm looking at Zoom. No volunteers. Atul, are you happy? Yeah. Okay, so in this case, let us obrigado our speaker again. Thank you so much for your very dangerous talk. Let me stop recording.